The next few videos focus on directed graphs, or digraphs for short. These are the graphs where all edges are directed. So there's an order to edges. We have an edge AB. This means that we have an edge from A to vertex B, but doesn't mean that we have an edge from B to A. So we have a way to get to B, but not to A if we're given only this edge. We know for them that if we have a simple graph, which we're always going to consider simple graphs, that the number of edges that we have is quadratic in terms of the number of vertices that we have. And we can always access for a particular vertex which edges are incoming and which ones are outgoing, so we can distinguish them this way. For example, C has outgoing edges to E and to D, and an incoming edge from A. So if we were to start at vertex C, we can only immediately reach E and D. From C, it's not possible for us to directly reach A. We would have to go kind of roundabout in order to get to it. There's a lot of applications which use digraphs. For example, we have one-way streets. We can only go one direction down it, or with flights, or also with task scheduling. So for example, we have a set of tasks and some prerequisites to them, and we can list out each task as a node, as a vertex, and then add an edge between them from A to B if task A is a prerequisite for B, if task A must be completed before task B. So for example, I have here the subset of scheduling of classes that we have in computer science and their prerequisites. So for example, before you can take algorithms, you have to have already completed CS2 and Calc2. So we've got an edge from CS2 to algorithms and Calc2 to algorithms. So another problem with digraphs is finding an ordering in which tasks should be completed so that we satisfy all prerequisites, and we'll figure out how to do that in one of the next videos. Now, one problem for digraphs is their reachability information, because we might have a path between vertices, A and B, but we don't just have any path, we have now a directed path. So this could mean that we can reach B from A, but we might not be able to reach A from B. So one question becomes, is it even possible to reach some vertex from another one? Or what set of vertices are reachable from a starting point? Now we can specialize the graph traversal algorithms that you've seen already, depth first search and breadth first search, in order to make them applicable to digraphs. And this is done by only traversing edges along their direction. So for example, if we started at vertex A, we could follow outgoing edges to B, E, and C, but we would not be able to follow this incoming edge. So we can use the same depth first search and breadth first search algorithms that you've seen, but rather than considering from a given vertex all incident edges, only considering outgoing edges so that they're followed along their direction. Now remember that breadth first search and depth first search, as we had discussed them on an undirected graph, gives a direction to edges to indicate how we encountered a vertex. And so we have two different kinds of edges. Well, since we're starting with directed edges to begin with, then in a directed depth first search algorithm, we'll get 4 different types of edges. So if we have some edge, let's say E, which goes from vertex U to vertex V, so this is that edge. We could classify this as either discovery edge. This would be the same that we're encountering vertex V for the first time, it hasn't been visited, and this edge is the edge which is discovering V for the first time. Or as a back edge, and this is how we distinguish the non-discovery edges is if we look at the spanning tree rooted at some starting vertex. So let's say we started at vertex A and we performed our directed depth first search starting from A. And we have here our discovery edges shown in dark blue. For all of the other non-discovery edges, we can classify them based on whether this edge has that V is an ancestor of U in this tree rooted at our starting vertex, or it's a descendant of U, or it has no relationship with you. So for example, we have some edge from D to A. A is the ancestor of D, so this is a back edge. We're starting from a vertex, D, and we're going back through the tree to a vertex which is an ancestor of that vertex. Forward edges do the opposite. They start at some vertex and they go forward, kind of skipping forward through the tree. So we're going from an ancestor to a descendant. So this is a forward edge. And cross edges connect two vertices where one of them isn't a descendant of the other one. So neither C nor E is an ancestor or descendant of the other one. And same for D and E. So these are cross edges. So a directed depth first search algorithm can have any one of these, but if we adapt breadth first search to work on a directed graph, just because of how we use breadth first search, then with breadth first search we wouldn't have these forward edges, because breadth first search will immediately find those vertices first. Those would be our discovery edges. Now, a directed depth first search starting at some vertex S will give us the vertices that are reachable from that vertex. So we'll still get a spanning forest, but each spanning tree doesn't represent a connected component. Instead, it represents a set of reachable vertices. So for example, for this given graph, we have on the top right here the spanning tree rooted at C. This represents all of the vertex that we were able to reach starting at vertex C. We weren't able to reach B or F because we didn't have any directed edges which went that way. Or here we have the spanning tree rooted at vertex B. So this is everything which is reachable from vertex B. This is useful in a variety of applications. For example, in program control flow analysis, where we have vertices represented by lines of code and an edge connecting them if from one line of code we can reach the other one, either through a function call or a control flow statement. And then if we have any vertices or lines of code which can't be reached, which have no way of getting to them, then this would be dead code, and we could safely eliminate it, get rid of it. It would have no impact on our program. This is also useful for garbage collection. So we have vertices which are objects, and if they are using another object or referencing it, then it has an edge to it. If some object is not reachable, it has no edge to it, then these are unused objects which can be safely removed from memory. Now, for undirected graphs, we had defined this notion of connectivity. So an undirected graph was connected if between any pair of vertices we had a path which connected them. Now, when we're working with a directed graph, we have to define this a little bit differently, because we could have a path, but this would be a directed path. So this doesn't exactly mean the same thing, that we have a path, but this doesn't mean that from this vertex we could reach the other vertex. If we want to give that same meaning, we'll call this strong connectivity. That means that between every pair of vertices, there's a way for this vertex to reach that one, and there's a way for this vertex to reach that one. So we want to figure out if a graph is strongly connected. Well, we know that the directed depth first search or breadth first search, this would give reachability information. So we could call DFS n times, once for each starting vertex, and check to make sure really the set of reachable vertices from it includes all of the other vertices for each vertex. But there's a better way that we can go about this, a better approach. Rather than running DFS from every vertex, we can only run DFS twice. So pick some arbitrary starting vertex. So this is our just any vertex in our graph. And then run depth first search from this vertex in the graph. Definitely, if the graph is strongly connected, then we should be able to reach all other vertices in the graph. So if at any given point in time you find that from this starting vertex there was some other vertex which was not reachable from it, then we can immediately print out, no, this is not a strongly connected graph. Otherwise, this vertex can reach all other vertices. Now, create a different graph. We'll call it G prime. This is our original graph, all of the same vertices and edges, except all of the edges are reversed. So we can do this in big O of M time just by reversing all edges, all of the M edges. Now in this modified graph, run depth first search from the same starting vertex. So if this vertex can reach all other vertices in the modified graph, then that means in the original graph, all of those other vertices could reach starting vertex V using those same edges. So for example, vertex F can reach A because in this modified graph, A can reach F along this path, which means in our original graph, F can reach A along that path since all edges are reversed. If there was any vertex that our starting vertex couldn't reach in this modified graph, we print no. That means that in our original graph, there was some vertex which couldn't reach our starting vertex. Otherwise, if our starting vertex can reach everything else, then we don't have to keep running depth first search because this immediately means that all vertices have a path connecting them to every other vertex, that every vertex is reachable from every other vertex. And the reason for that is we've got, here's our starting vertex V. In the first step here, it's established that V can reach every other vertex. And in the second step, it's established that every other vertex can reach V. Which means that through V, each vertex, say X and Y, can reach each other. X can reach V and V can reach Y, and Y can reach V and V can reach X. So we've got a path from X to Y and a path from Y to X through this vertex V. So the total running time is big O of N plus M, which is the cost of depth first search. And this is because we only call depth first search twice. A graph can be broken up into a directed graph can be broken up into strongly connected components, which are maximal subgraphs that are strongly connected. This can also be done in linear time using depth first search, kind of how we did with biconnectivity, but a little bit more complicated. But this is just breaking up the original graph into maximal subgraphs so that all of the vertices in this subgraph are strongly connected. They're reachable to every other vertex in that subgraph.